Please, yeah, the floor is all yours.
Okay, so thank you, Guillermo, and also nice to see this audience. In fact, I see one co-author of mine, Lloyd Humberstone. I hope he is actually present, which reminds me of the good old days in the 1980s, as I was a young aspiring logician. In fact, reminding of the good old days, I have a somewhat historical but also current topic, as you can see from my title, Logic and Natural Language. Yeah, maybe that's also fitting for an event that has to do with World Logic Day, because you could think of that as a sort of anniversary of a subject that has existed for a very long time. So what I want to do is talk a bit in general about connections between logical languages and natural language, and then talk about a specific topic, namely monotonicity inference. And then I hope I can show you that that topic actually is very relevant today, and that raises lots of interesting issues. So let's see if I can, yeah. So let me start with natural language and logical languages. So here comes what's probably the textbook story about how logic arose in the first place. So I mean logical theory, namely that people started realizing that there were certain patterns in formulated in natural language, patterns of inference, some of them valid, some not. Or if you want to take so as an example of such a pattern, right, let me just remind you, I hope I got this right, by the way, that this one is valid. All children left early, no musician left early, therefore no musician was a child. So the pattern here would be that of a typical syllogism. So we have two, what we would call quantifiers, all and no, and there's a certain pattern of distribution of the predicates child, leaving early, and musician. Now, if you take a broader historic perspective, you could say, well, of course, logical reasoning itself must be much older. So in my imagination, I think of our ancestors in caves planning the hunt and still engaging in logical reasoning, like if the saber-toothed tiger isn't if it can be in only one of two places and it's not here, then it must be in the other one, and so on. So that practice must be very old. But the next stage is seeing patterns, like seeing a pattern in the example which I just gave. And the next stage, you could say after that, is finding rules behind those patterns or that connect those patterns. And of course, eventually, a discipline arises that gives a systematic theory. This is actually, as a sort of aside, an interesting way of thinking about intellectual history in general. There's a book by my colleague in Amsterdam, Rens Bot, which you see to the left, which is actually about this sort of four-stage sequence that you can find in lots of topics in the humanities and sciences. And he actually uses that to think about the development of world culture, world intellectual culture. And of course, logic itself is a good example of world intellectual culture, since, as I'm sure you know, it has arisen in different cultural traditions. So, of course, there's Aristotle, who you see here on the Greek stamp, and that's the tradition we're all steeped in. But what fewer people know is that also around the same time as Aristotle, there was a Greek logic tradition around Moze, whose picture you see there, which we're actually studying in the Beijing Center that I'm involved with. And of course, there's the traditional Buddhist logic see my picture to the right. So we're in a field with a long history. We're in a very international cultural field, and it all has to do with these practices, patterns, rules, and eventually theory. Now, you may think, even if you think that you find these patterns in natural language, there's also something about natural language which may be not ideal for seeing those patterns. So natural language differ in syntax. They also vary over time. In fact, sometimes the grammatical changes can be very fast. But we all feel that what we're really after is the meanings, or on another philosophical view, the thoughts or the propositions that are manipulated in reasoning. So it's those things we'd like to believe that are expressed and communicated using natural language. And throughout the history of logic, people have actually thought, well, that must mean is that underlying natural language, there must be a more stable level of what's actually meant and what's actually conveyed and what's actually manipulated in inference. And that stable level has often been called logical form. Now, my talk today is not about the history of logical form. There's actually in the textbook, the Gamma textbook, Logic, Language and Meaning, there's a whole chapter on this history from antiquity until now on this notion of logical form, but this in the background. So now let me remind you of the way, let's say, my colleagues would teach logic, and if you teach an introduction, and you probably also do something similar. So in the 19th century, what we see is the emergence of full-fledged formal languages of the sort that logicians use, like for first-order predicate logic and so on, and sort of complete systems with their own syntax, their own rules, and so on, and written with the famous formulas, with, of course, invented by the famous pioneers like George Boole, who you see here, Gottlob Frege, and roughly at the same time, Charles Saunders Peirce. And what that means is that once you have these formal languages, there's actually a sort of two-level thing that you can do when you think about these inference patterns. So you could say, if I just look at the natural language, then I have a sentence, let's say sentence number one, and as a sort of natural process, I see that I can infer sentence two. But the way we analyze that is that we translate into a formal language level. So we translate sentence one into formula one. That's the topic of a lot of the exercises that we do in the elementary logic courses. Then at the level of the formulas, we can actually use formal tools, like we derive another formula two from formula one, using some logical proof system or whatever systematic theory that we have. But we can still connect that second formula back to a sentence. So what you get in this way is a sort of diagram. This is a diagram I've taken from a very recent paper by Larry Moss and Doug Westerstahl, who are trying to reflect on what it is that we're actually assuming when we follow this educational practice. And what they say is that in some sense they think of this as the top level, so inference between sentences in natural language. That's a sort of empirical phenomenon, which you can actually see happening. And what the bottom level does is, with the formulas, it's a sort of scientific theory, which tries to model these empirical phenomena the same way other scientific theories model other empirical phenomena. And of course, you'd like the theory to be in tune with the phenomena that you're describing. So what they say, and that's a typical mathematician's notion, they say the diagram which I've sketched here should commute. In other words, you'll be in tune with your formal language analysis of the natural language if the following two roads lead to the same goal. First, you go down and translate a sentence, then you apply your logical calculus to derive formula two. That should give the same result as first you follow your natural inferential practice from sentence one to sentence two, then you translate sentence two. If that ends up in the same place, that's the commuting diagram, then you're on track with your logical theory of what the natural language inference is doing. I'm also not going to discuss this more. The paper will appear, I'm sure, but it's interesting to think about what we actually assume in this practice, whether this or something more complicated. Now, once we had the natural and the formal languages, so that's maybe around 1900, You can see various positions in the philosophical literature on how we should now view the relationship of logic and natural language. So some people, you could associate that with the early Carnap, maybe also the early Wittgenstein, would say that the formal language is better. It actually gives a better insight into either the structure of our concepts or the structure of the world. So you could even think of it as replacing natural language. So that's replacement. But then, of course, there was a reaction to that, especially in the 1950s in the Oxford-style analytical philosophy, where natural language made a comeback, and where actually the natural language is considered richer and in some sense better than the logical languages, like in Austin's famous expression about natural language. There's gold in them, there are hills. So the natural language has a lot to offer, which formal languages just cannot do. My personal position is in between those two extremes. I think that if you look at practice all around us, what we actually see are combinations of natural and formal languages. Even though we have lots of formal languages, they've never managed to replace natural language. But on the other hand, you see a lot of extension of natural language with formal language as soon as some practice requires this. So this is clear in mathematics papers. It's clear in computer science. And I might even add that it's also clear, though to a lesser degree, in other expert practices like the law and so on, where sometimes you find pretty formal notation, even logical variables, to make it clear what a legal contract is actually saying. And in fact, there is an area which is a typical meeting place of the two viewpoints. So natural language as a natural phenomenon and formal logical languages, namely the area of formal semantics, where you study linguistic phenomena with formal mathematical models, and where you use logical systems as perhaps not complete, but the sort of scientific models of reasoning practices. So a few sources are indicated here. The Handbook of Logic and Language has a lot. And of course, a lot of this was triggered by the work of Richard Montague. So I put a famous collection on Montague grammar. And a good example of a topic which is in a sense in between, which you can look at both from the viewpoint of natural language and from the viewpoint of formal languages, is quantifiers. A lot of this research was triggered by prominent linguists who actually became interested in adding the logical perspective to the linguistic perspective, like the picture you see here is Barbara Partee, who famously said that inferences are part of the linguistic data. So logic has to be there in looking at the natural language. And the result of all that work was the area of generalized quantifier theory, which you could think of as a sort of joint offspring of logic and linguistics. By the way, joint offspring, I think, is the best recipe for interdisciplinary contacts. So people often think that when you work together with another field, you're like a sort of doctor. You're going to heal their wounds and help them get rid of their diseases. That will never work, I think. So in trying to improve a subject, but finding something new to do together, that seems to me a success formula. By the way, this is completely irrelevant. I sometimes find myself wondering about the word formula, because as you know, this is the Latin diminutive for form. So we have the grand forms that we're looking at in logic, and formulas are little forms. Somehow, my mind sometimes wanders to how we got into that terminology. Now I want to do a case study. That's the main part of my presentation, which is still seems to me very relevant, of looking at an inferential phenomenon from the viewpoint of natural language and logic at the same time. And I'll take the case of natural logic and in the more specific case of monotonicity. So what we teach in the logic course, if you think of my diagram, might be that in order to study the behavior of a certain reasoning practice, we first have to do this translation level, study it at the level of our logical model in a first order language or some other formal language, and do our logical type of analysis, and then maybe go back to natural language to check with the commutation in the diagram whether we're still in tune with the actual phenomena. But there's also an interesting question, which is how much reasoning could we actually do on natural language itself? So is it always necessary to make this excursion towards the logical form or the formula form? And assuming, I'll get ahead of myself, that this is sometimes possible, but not always, the second question would be, where is the transition to formal language really more profitable? And this type of interest sometimes goes under the name of natural logic. That's a sort of play on natural language and logic. And I myself became very interested in that in the early 1980s for various reasons. So I'll skip the computational linguistics. And well, I'll just mention this second point, the creative reactionaries. So around 1980, and I guess probably still today, there was a sort of small trickle of authors who actually thought that there was something strange or perhaps even unfair about replacement of traditional Aristotelian logic by modern logic, because they thought traditional logic actually had a much better fit with natural language, and it could also do a lot. So it was quite successful in its own way. So how could it be that these formula-wielding, more mathematically inclined logicians won the day, and that's so fast? Famous example of this is a book by Fred Sommers, The Logic of Natural Language, which some of you may know, and which I read as a student and which I found extremely interesting. Well, I've published a bit on this natural logic. I wanted to talk a bit about it. So here's a ubiquitous inference pattern in natural language, monotonicity. So for instance, suppose that you know that all boys danced. Then you can conclude that all boys moved. What I'm doing there is I'm replacing the predicate dance by the predicate move. I call this an upward replacement because the predicate dance is included in the predicate move. Or describing it a bit differently, I've replaced the more specific predicate dance by the more general predicate move. These replacements can be upward, but they can also be downwards, because in the same sentence, all boys danced, it follows that all Dutch boys danced. But of course, Dutch boys isn't more general than boys, it's more specific. So I go down from boys to the more demanding predicate Dutch boys, downward. And the same sort of replacement inferences can also be seen with other quantifiers, like some boys danced, so some Dutch boys danced, or some Dutch boys moved. No boys moved, so no boys danced, and so on. So these replacement inferences can be upwards by broader predicates or downward by more specific predicates, and it depends on the position. Monotonicity inference is very frequent, if you think about it. And it's very interesting because it's so obviously valid, and it's also so fast that you usually don't have to spell it out. So it's with us as soon as we use natural language. Say I'm walking somewhere with my son, and a sign says children not allowed, right? And I immediately realize that the presence of my son is not allowed there. That's not because I go through some complicated inference. That inference just, is in my mind immediately with the thought that I'm walking here with my son. Plus, of course, what the sign says. Okay, a bit about the general pattern here. So the quantifiers in natural language, you can think of binary predicates to a first approximation. So there's a Q expression like all, some, no, and then there's two predicates, A and B. You could think of this as in line with the sentence pattern that you can rewrite a sentence S to an MP, a determiner, a noun, and a verb phrase. So the determiner is then the quantifier expression, the noun is the first argument A, the VP is the second argument B. And monotonicity inferences are about predicate replacement. So in a set theoretic notation, for instance, if you have QAB, B is included in B prime, conclude QAB prime, that would be an instance of what you might call right-up monotonicity. It's on the right because it's in the B argument, and it's up because you can replace B by a predicate with a larger extension, and so on for the other combinations. How do we think, say, in formal semantics about these quantifiers? Well, you can also form a visual image. So you have two sets, A and B, written in a Venn diagram, and the Q, A, B. So there's some relation. Some of these sets will be in a required relationship. This is, of course, all basic logic. I'm just trying to give the framework that I'm using in thinking about these matters. You could have several views of what quantifiers mean. Take all A or B. You could think about it set theoretically. Then in terms of the Venn diagram, it says that the area A minus B is empty. But you could also think numerically. After all, quantifier means expression of quantity. So I've put in two red small a, they actually stand for numbers. So the small red A is the number of things in A minus B. The small red B is the number of things in A intersect B. And you could also say that all A, B actually just has a numerical meaning. What it says is that the little a equals 0. The same can be done for other quantificational expressions, but this is the style of thinking in what follows. Of course, there's many other quantifier expressions in natural language, so I've listed a few for you, but there's huge lists of expressions. You can count specific numbers. You can combine the numbers with the classical quantifiers like all A but one, all A except the B's, most, many, enough. Some people sometimes tell me, yes, that's all, or some students even, that's all very interesting, but maybe these are very rare expressions. So what is this subject of logic actually interested in? But what I would recommend to you if you are confronted with such students is look at a frequency list of expressions in English, and you'll actually see that the logical expressions are high up in frequency lists. So some of them are in the top 10 of most frequent expressions in English. And that's not just English, because the same is true with frequency lists for Chinese, for instance. So again, on this monotonicity behavior, well, for instance, think of the classical square of opposition. So the quantifier all, as we just saw, has a sort of double monotonicity behavior. So it's downward in its left argument. So look at the downward arrow, and it's upward in the right argument. Okay. Sum is upward in both its arguments. No is downward in both its arguments. And then to fill the final corner, not all is upward in its left argument and downward in its right argument. In what follows, I will mostly write the down arrow as minus and the up arrow as plus. So you could say that if you look at the classical logical quantifiers, they are inference rich. They actually allow you to infer a lot. And that's even one view you could have of the classical logical constants. You can have lots of views of them. You can think of them in terms of invariances or easy computability or whatever. But one way that what's so special about them is that they allow or trigger lots of inferences. However, monotonicity is not confined to the basic first order quantifiers. Think of an expression like most A are B. Most A are B is actually allows monotonicity behavior in its right-hand argument. So if most A are B, and if I replace B by a larger predicate B plus, it's still true that most A are B plus. So most A are B is upward monotonic. It allows these inferences in its right-hand argument. On the other hand, you can easily convince yourself that, unlike with the first order quantifiers, most A or B does not have monotonicity behavior in its left-hand argument. So if most Dutchmen like soccer, it doesn't follow that most Europeans like soccer, right, as an example. But it's also, so it's certainly not upward, most A or B from A to something larger. But it's also not necessarily downward, because even if it's true that most Dutchmen like soccer, it doesn't follow that most soccer-hating Dutchmen like soccer, right? So you go to smaller predicates, soccer-hating Dutchmen, and it's no longer true. But there's still some inferential behavior. Of course, monotonicity is not the only widespread pattern you find in natural language. Here's another one much studied in the semantic literature called conservativity. So formally what it says is that the quantifier relation Q holds between two predicates A and B, even only if it holds between A and the intersection of B and A. So if you want that in words, think all men are mortal, classical example. That's equivalent to saying all men are mortal men. Right? So you restrict by conjunction the predicate mortal to mortal man. In other words, you could say in quantifying expressions, the left-hand argument sets the scene. The objects outside of A do not matter. This is actually very common in general restrictions. So in more empirical semantic research, you find sort of broad agreement with this property in all natural languages. Conservativity actually isn't just this. You could think of it even as a sort of more general role restriction, but maybe I shouldn't go into this. In fact, if you're interested historically, and if you know something about Peirce's work on existential graphs, you'll actually see that one of the important rules in Peirce's system, the copying rule, is actually a sort of general principle of conservativity. Sorry?
I'm sorry.
I'm sorry, I'm hearing a comment or a suggestion. Please interrupt me if you have something to say or ask.
No,
No?
Johan, I think that was by accident. I think.
Okay, no problem. No problem. Yeah, but Guillermo, you can give me feedback if you feel I'm going too fast or too slow.
No worries. I think you are going at exactly the right speed.
Okay.
Yeah, no
Okay. Okay. Okay, and if you think numerically, if you go back to my Venn diagram, what conservativity actually does, I'd already more or less assumed it here, is that it's only those numbers little a and little b that matter, because they only look at what's in A, right? What's in A but not in B, and what's in A and what is in B. Maybe a bit more about numerical content of quantifiers. Of course, I could bring in the other numbers as well. So then A, B, and also so I have small c and d. And I've written a few quantifier meanings for you in these terms. For instance, most A or B actually says that the number little b is greater than the number little a, at least to a first approximation. There are some other uses of most. Many A or B, I'm just displaying that looks much more complicated. We could talk about it in discussion. This is actually from a paper by Doug Westerstahl in 1980s. There's a sort of proportional sense of many, which actually does involve all the four numbers that I'm talking about here. The point is just that a lot of these expressions support monotonicity inferences, maybe not as many as the basic logical quantifiers, but still quite a few. So in some sense, monotonicity is a very general phenomenon in natural language, and natural language doesn't put a fence around some sort of small set of standard logical constants. Now, there's a long history to monotonicity, which I won't go into here, because I want to get to more recent topics, but let me just make two bold claims. One is that Aristotle's syllogistic is largely about monotonicity inferences, where all or no type premises give the inclusion statements which tell you that one predicate is larger than another, and you apply that to the second premise in the syllogism to reach the conclusion. The same case has been made for examples studied in ancient Chinese logic by my colleague Fen Rong Liu and her students in Beijing, that a lot of the examples that they came up with, the early patterns that the Chinese logicians looked at, are monotonicity patterns. And the second bold claim, medieval logic tried to extend the syllogistic. That's certainly true. They had sophisticated approaches like distribution theory. And from a modern point of view, you could think of that as a move towards general monotonicity reasoning. But there was a sort of problem, namely how to deal with monotonicity inferences when you have complex syntactic constructions. And that brings me to why is monotonicity an example of trying to do inference in natural language? Well, with my examples, what I'm suggesting is that we can actually look at these inferences just in natural language as it is. There's no need for writing formulas. In fact, in one of the papers I wrote about this, I did give the first order translations, but from my point of view, that doesn't even help. I don't think the monotonicity inference is clearer in first order notation. In fact, if anything, it's less clear than when you just look at what happens on the natural language side. But how can we study this more generally? And well, then what we have to take into account is two things. The examples of the quantifiers I've given you give lexical information. So we have monotonicity information about key lexical items like quantifiers. In fact, not just quantifiers, I won't have time for that today, but many other types of expression, adverbs, adjectives, and so on, can have a monotonicity behavior. But that's lexical information. But sentences, of course, on the whole, are constructed in more complex ways with lexical items, plus some sort of construction principles. Say, with iterated quantifiers, right? So they are not of the pattern QAB, which I just gave, but they could be of the pattern Q1A, your first quantifier, and R, a relation, then Q2B, a second quantifier. For instance, suppose that you do know the lexical monotonicity behavior of Q1 and Q2. How can you predict the monotonicity behavior in such complex sentences? For instance, take an example. What are the plus-minus markings? Plus for upward monotonicity, minus for downward, in a sentence like "No man slays every dragon." This is an old example. I apologize. I don't even know exactly what where it comes from. Maybe some Harry Potter novel, but in any case, I should probably put something else, but it will do for technical purposes. For instance, ask yourself, so there's two quantifier expressions, no man and every dragon, and just look at this as a natural language sentence, so don't translate into first order logic, and ask yourself, take the predicate man, is it upward or downward? So can I replace man by human? So if no man slays every dragon, does it follow that no human slays every dragon? And the answer is no, it's not upward, because there might be a woman who is capable of doing this. So it's not upward, but it is downward, right? So if no man slays every dragon, it follows that no Dutchman slays every dragon. And you could look at the same for dragon. Actually, if you think about that, you're going to see that it's upward. So if no man slays every dragon, then it follows that no man slays every mythical animal. And the monotonicity even applies to the verb, slays, right? So you could ask yourself, is that up or down? Well, I leave that to your intuitive. How can we think about this more systematically? Well, Gauck's monotonicity markings you could think of as coming from the syntax tree that constructed the sentence. So let's take a very simple one for this sentence. We have a sentence S. It gets rewritten to NP and VP. So the NP is no man. The VP is slays every dragon. The NP rewrites to a combination of a determiner, in this case the quantifier expression no, and the noun man. And the VP rewrites to a transitive verb, slays, and then another noun phrase, the object of that, every dragon, which again has the same pattern. It rewrites to a determiner and a noun. Now, if we look at this tree, we can see the following things. So I'm just giving an example. I'm not giving the whole calculus. As a sort of general principle, when you rewrite a linguistic expression, there's often going to be a head and a non-head. So for instance, if you write S to NP, VP, the NP is the head. So what I'll just posit, I could also argue for it, is as a sort of general view that the head in such a rewriting is in positive position. So that's why I put a plus for the transition from S to NP to the top left. In rewriting the NP to that N, the determiner expression is the head, so I'll write another plus there. If I just go by the heads, look at the color for that, you will see a similar sort of plus from the VP to the NP, and then again from the N to the right, from the NP to the right to the determiner. So those 4 pluses just come from the syntactic construction and locating the heads. What about the other things that we see in the tree? Well, that's where the lexical information has to come in. For instance, the determiner to the left is the word no, and we know that no makes both its arguments downward. How do we see that in the tree? Well, the first argument of the no is this rewrite from the NP to the N to the left. So I've put a minus there. That's not because of the syntactic construction, but it's because of the lexical information about the no. So by putting a minus there, I've let the expression no make that transition negative. Where's the other argument of the no? Well, it actually sits on top to the right from the S, right? Because it's no man and then slays every dragon. So that's what the VP says. So I also put a minus in the transition from the S to the VP. And in a similar way, the determiner every, which you find down to the right, actually is responsible for the other 2 red markings which I'm giving. It puts a minus from the NP to the N and a plus from the VP to the TV. There's various algorithms for doing this. What they all have in common is you need some sort of natural language syntax, and then there's various very fast and efficient ways of putting these markings. And now, once we have these markings, I can actually compute what the inferential behavior is of the various words in this sentence. Let's take the example of man. So man is this noun phrase to the left, and it sits at the end of a history which runs as follows. You go from S to NP, that was plus, and then you go from NP to N, that was minus. So there's a path of unbroken markings, plus, minus, and I hope that you'll agree with me, this is what you expect, that a combination of plus and minus has to be minus. Similar thinking about the transitive verb slays, that's a path minus plus, first S to VP, V to P to TV, so minus. Then let's say dragon. Dragon goes, first you have a minus from S to VP, then you have plus from VP to NP, then you have a minus from NP to N, minus times plus. I hope again you'll agree that's minus. So then we get minus plus minus, and that equals plus. So it's a sort of simple polarity count. That accounts for the markings and the monotonicity, possible monotonicity inferences on man, slays, and dragon. Interestingly, the tree has more information. it even marks the occurrences of the quantifiers or the determiners. For instance, the first word no, if you look at its history, it comes from two pluses, so it's plus. So that means that in principle, I could also do monotonicity inference on the no position in the sentence. And that's true. For instance, if I were to weaken the determiner no to something like no, or maybe just one, think of that as weaker determiner. It's certainly true that if no man slays every dragon, it follows that no, or maybe just one man slays every dragon. So in a sentence like this, in fact, every position in the sentence allows for inferencing of the monotonicity kind. So in my didactic jargon, many natural language sentences are inferentially ticklish. Wherever you press, they do something, either upward or downward. So two components, if you want to get this into a calculus, specific information about lexical items like the quantifiers, and the monotonicity effects of syntactic composition. To make this work, you can use your favorite linguistic grammar formalism or closer to logic, like I myself, when I started writing about this in the 1980s, used categorical grammar, where it's actually most useful to do it in the Lambeck style. Actually, as a small aside, but very quickly, of course, this polarity count is not just typical for monotonicity or logic. In some sense, it governs human history, right? So friends of my friends are my friends, enemies of my enemies are my friends, friends of my enemies are my enemies, enemies of my friends are my enemies. If you understand that little rule, I think you understand most of human political history, even today. Now, so that's all I wanted to say about how you could think about how monotonicity inference works on natural language. So you have the natural language expressions. There's a simple type of inferencing with replacement by weaker or stronger predicates, depending on what type of position it is. And if you think of how do I find out what types of position I'm talking about, I need to do a little syntactic sentence analysis, as in this monotonicity calculus, where I need two things: the specific information about lexical items, what sort of inferences they favor, like in the quantifying expressions, and I need a sort of story about the syntax and how monotonicity markings, that is inferential markings, actually get combined until they reach the surface. By the way, notice that in terms of computational complexity, this process is extremely fast and efficient. So, because by working on the syntax tree, actually I can get the monotonicity information for free, just in the parsing stage. So if I understand the grammatical composition of a sentence, I automatically understand the inferential behavior, at least as far as monotonicity is concerned. So you could think of monotonicity reasoning as a very fast inferential subsystem that we have available, and it costs nothing because it just comes together with understanding the sentence. So that was my introduction to monotonicity reasoning, and as a sort of species of reasoning you could do in natural language or close to natural language. And the rest of my presentation, I think I have about 15 more minutes maybe before discussion time. Is that right, Guillermo?
Yep, that's correct.
Yeah. I'd like to talk you through a few contemporary issues raised by this whole subject, because it's still very much alive. Maybe first just quickly, so some of them I'll just do quickly. Sort of historical aside. As I said, monotonicity is at the heart of classical traditional logic before the 19th century. So in the Aristotelian syllogistic, also in the medieval theory of distribution. Now, what we're often told is that traditional logic was inadequate and so maybe even in some sense deeply flawed. I remember as a student reading Peter Geach's book, Logic Matters, where he actually describes the realm of traditional logic as the kingdom of darkness. So full of confusions and evil, even the source of evil thinking. Was that really true? Well, this negative judgment is often backed up by sort of saying, well, at best, this syllogistic is maybe just a trivial monadic fragment of first order logic, something like that. But I think that does no justice to what I just said, because the monotonicity inferences, for instance, they work on natural language. First, they're not confined to first order quantifiers or something like that. And even they can work on whole chunks, very complex chunks of natural language. For instance, if you say, no man loves most of the people present here, it's a very complex verb phrase, you can still have the inferential information about the man that it's downward, regardless of how complex this verb phrase is. So I personally think we should think of natural logic more as a sort of outside-in analysis tool for natural language. So we look at the top level at potentially very complex natural language sentences and apply it that way. So that only looks trivial or like a very small fragment if you have a sort of logical optimistic idea that natural language sense, it's all about building up inside out from simple components. But I don't think that's the way you should think about inference in natural language. Of course, that's not to say, so the second point between this monotonicity inference in natural language and formal logic, because formal logic can definitely inform natural logic. So in line with this view that what we do with formal languages is provide models and hopefully illuminating models of what goes on in natural language. And of course, now I get on familiar ground. Most of you will know that, for instance, if you specialize to first order logic, there's a lot we know about monotonicity. First, we can define it very clearly. So, so if phi of p, so a formula with occurrence of the predicate p, is true in a model under some assignment, and we replace p by a larger predicate, then we have phi of q. That's a precise definition of what we mean by the validity of the upward monotonic inferences. We also know that a trigger for this is positive occurrence under an even number of negations, or being able to write it in a syntax where the predicate that we're talking about only occurs positively, the predicate P. We have Linden's theorem from the 1950s, which even says that these two viewpoints are at least extensionally equivalent, so that a first order formula phi of P is semantically monotone in P, even if phi of P is equivalent to a formula with only positive occurrences of P in the syntactic sense. And we could also use formal logic to make my earlier statement more precise, that the complexity of monotonicity reasoning is decidable in P time, which actually makes it quite different from the undecidability of first order consequence in general. So I don't think of this as an opposition. The formal logic actually sheds light on the natural logic. So that was my second point. And okay, here's another one that, it may be a bit of an aside. Many people who see natural logic get overexcited and they think, so here we have inference that we can do entirely on the surface of natural language. So it's pure surface inference. And even I myself have sometimes written about it that way. But that's not quite true. And there's actually some interesting issues here. So the syntax is still needed, not the pure linguistic surface form. Because if I just give you a string, a linguistic string, you may not be able to find out the monotonicity markings, or in other words, to feel the inferential behavior. Because without syntax, we get ambiguities that block all or some of the inferences. Take an expression, this is not a quantifier example, not cheap and attractive. If I don't indicate the scope of the not, then here's what I can say. I can resolve, of course, this scope in two ways. So it could be not cheap, science for a moment, and attractive. but it could also be not, silence, cheap and attractive, with a large scope for the not over cheap and attractive. Whatever, no matter how we resolve this, the cheap always gets a minus. So not cheap and attractive implies not very cheap and attractive. But the monotonicity marking for attractive would really depend on how we solve the ambiguity in the scoping of the negation, right? If the not scope doesn't scope over it, it's positive, and if it does scope over it, then it's negative. Now, in actual uses of natural language, of course, the context usually ambiguates, or for instance, we have the recording actually of this talk. If you listen to the two ways I pronounced the two scope readings of not cheap and attractive, there's probably cues in the phonetics of how I pronounced it that would actually tell you what the scope of the not is. So the context usually disambiguates. And that's my first question, which I actually don't know how to do yet. Could we bring in context systematically into fast, efficient calculi for natural logic? If you want to keep it efficient, context would have to come in a very simple and fast way. I don't know how to do that yet. On the other hand, there may be cases where context does not disambiguate, and that's still an interesting topic for discussion. Suppose that you have linguistic expressions like sentences or other expressions where we don't know all the scoping, for instance, or we only have partial information about the syntactic construction. Can we still do inference? And I think from a sort of empirical point of view, yes. But how should we set that up? That topic has been discussed in the semantic literature. So trying to do theories of inference that don't assume that every assertion you're manipulating is fully specified in terms of its syntax, but I mention it here as an open problem, like how to best do that. Then you may think, well, look, that's all interesting, this monotonicity behavior, but it's only one small part of reasoning. Maybe it's just some sort of exceptional thing. But I actually think that there are lots of fast inference modules in natural language, which you could also study in natural language. For instance, I already mentioned conservativity, there's inferencing with time and temporal perspective. And in recent work with Thomas Ickart at Stanford, I've also been looking at simple natural language inferences combined with counting or arithmetic. So just simple parts of logic, logical inference, simple parts of counting, calculating, and so on. I think there's a lot of these systems. Of course, another open problem, if you take that point of view, what is the architecture of natural language inference, right, as done on natural language? And again, I don't think we have a good general view of that. It would be very interesting to push such a project. And again, this is not in conflict with formal logic, because actually formal logic can teach us things like the following. Okay, you may have a sort of sunny expectations about natural language as consisting of a lot of relatively fast and efficient reasoning mechanisms of the monotonicity kind, of temporal reasoning, of restriction, and so on. But if we somehow, the way language functions, these subsystems must be able to communicate and pass information to each other. So they have to combine. And what we know from formal logic is that combining even low complexity inference systems can create very complex undecidable systems. So that's again something that I don't think has been explored in any depth, whether that sort of pitfall actually occurs in natural language. That, say, if you combine simple monotonicity reasoning with simple temporal reasoning, that you'd get a rather complex combined beast. Also, just in terms of the actual reasoning phenomena, of course, I'm not saying that every sort of reasoning can be done in this natural logic style. The monotonicity inferences were special. They take a free ride on the syntax, as I showed with my little syntax tree. They're fast, they're easy to compute. The calculus has a low complexity. But we also have full logical calculi, so which are about proof search and doing this and that of the kind that logicians know. They are needed when we want to describe slow, conscious search for complex pieces of reasoning that require not just the fast inference that you'd have available automatically, but that require proof construction. That's already true with simple examples like the Russell paradox. That may still look relatively simple, but it's definitely not a sort of fast conclusion you would reach from monotonicity reasoning. And it's, of course, definitely true for much longer formal arguments, say in mathematics. So, well, that's interesting. That means that you might think of a sort of division of labor where the fast inferential subsystems are actually dealt with at a sort of natural logic level, where you try to stay as close to natural language as you can. But at some stage, this has to interface with the transition to real heavy powered logical systems that can do the conscious reasoning and the proof construction. And that leads to lots of border questions. And I'm sorry for today, I'm not presenting theorems, although there's actually a lot of technical work on these matters, but just questions. So can we investigate this border traffic more precisely? For instance, one, we all are in the business of constructing formal logical systems for analyzing various notions of interest. That's most of what I do. But might it be true that these complex systems, like very complex epistemic logics or epistemic temporal logics, have simple natural logic fragments that live inside natural language? I don't think that has been looked at systematically. You could also ask yourself, suppose that I take, say, the monotonic fragment of first order reasoning, and if I still would like to have my standard logical concerns, are these fragments complete with respect to a natural semantics? This is a question which has been investigated, for instance, by Thomas Ickart and Larry Moss. Or isn't it very semantic? And do these fast natural logic fragments actually rather come from an operation on proof systems, so that we have a sort of simplified parts of proof, of complete formal proof systems that they exploit, and so on. Now, I'm almost at the end of my time, but I want to end with putting this whole topic of the monotonicity reasoning in a larger perspective. Here's one interesting thing, that everything I told you about this monotonicity calculus is largely from the 1980s, when, at least my own work is on it is from that time. But it's been rediscovered many times, or well, at least a number of times. One rediscovery was around 2000 in cognitive science and cognitive neuroscience, because people there were interested in the question whether there's inference modules in the brain. And what some people started publishing on it, this was at the Max Planck Institute for Psycholinguistics in Nijmegen in the Netherlands, was the idea that reasoning in the brain is actually not one thing. It's actually done in various areas of the brain. And there's areas that actually specialize in fast and efficient reasoning, and there's areas that specialize in slower and more conscious reasoning. And lo and behold, in that work, examples of the fast systems were exactly monotonicity reasoning, plus some beginnings of the calculus, which I just gave you. Notice as an aside, this is not the famous slow versus fast thinking of Kahneman, which you can buy in every airport as you're waiting for your flight, since there's piles of these books. Since the natural logic system that I'm talking about is fast, but it's correct. It's not a default reasoning mechanism. It's just a fast system for correct inferencing. It's not a vehicle for informal jumping to tentative conclusions. So that's rediscovery number one. Rediscovery number two, in the area of computer science. So in the 1990s, natural logic again was rediscovered independently in work on natural language processing and information retrieval. And the way it came up there was that information retrieval started by just looking for keywords. So suppose that you're interested in terrorist incidents. You look at a lot of newspaper articles and you're doing keyword search. So you're looking for terrorism or maybe incident. But then it occurred to people that they shouldn't just look for keywords, because suppose that actually in a text you have an expression like, you know, a bombing episode, right? That's a terrorist. That's a terrorist incident, presumably, and but it's not literally that keyword. It's rather that you know, the bombing episode is a special kind of terrorist incident. So basically you can think of this as the text that you're looking at. You're not just searching for the literal words that you're interested in, but you're also searching for words that would actually allow a monotonicity inference to an expression with the words that you're interested in. Yeah, so there were various groups that actually worked on what you might call natural logic, importing that into information retrieval systems. Now I'm almost at the end of my story, because I don't know how this is in Australia, but of course, nowadays as a logician language, one is often confronted with people who say, yeah, but that's all talk of the past. Because nowadays we have large language models like ChatGPT and so on. And these things produce huge state spaces that look unlike anything that logicians have said. So in other words, you know, you could close the books of the history of this thinking about either natural logic or maybe even formal logic. And, you know, because the large language models just don't do it like that. So now I'd like to end on an optimistic note here, because again, the monotonicity is relevant here. So there's some recent work by colleagues of mine at Stanford, Atticus Geiger, Thomas Eckart, and Chris Potts, who actually changed this discussion to the following. So of course, if you take a large language model like BERT, you know, it produces hundreds of billions of variables. And it's true that in the state space of that system, you're not going to see anything that looks like either standard linguistic theory or standard logical theory of inferencing. But that may be the wrong level to look at, because in that's the top level description of the state space produced by the system. But as an object, that system has lots of information reductions. So what are information reductions? They're ways of grouping the variables into large groups, defining a new structure on those groups. And then, so in some sense, projecting the information in state space into much smaller state spaces with huge groupings of variables now acting as a single one. Now, of course, you could do those reductions in lots of ways that are maybe not so interesting, but a few years ago, there was a paper by Beckers and Halpern, which actually produced a principled notion of causally faithful information reduction of state spaces of machine learning systems. So that's, of course, a conceptual advance of a few years ago. And what Geiger, Eckart, and Potts were able to show was that if you causally faithfully information reduce the full space of BERT, a famous large language model, you'll actually see that it has actually learned the monotonicity calculus. In other words, if you look at large language models in the right way, again, you're going to find familiar structures of the natural logic sort inside what the system has learned. So think of that as my positive message. Everything I've told you is still quite relevant in the world today. So my conclusion: combining natural and formal languages in the study of inference is well motivated and well worth studying. And I think it leads to all sorts of new questions. Of course, I'm doing that as a logician, so I'm not doing it as a linguist. But I think that if you do that, you get interesting new perspectives on the functioning of natural language, but also through these more recent developments, cognition and computation. And given the connections that I made with the syllogistic and medieval logic, it may even lead us to reevaluate the history of logic itself. And I'm going to stop here.